take you to practice quiz, problem number 1. List the known series that converge. Any series that you know that converge. You could start by listing examples, but eventually I want the name of the series as well. So I left on Thursday morning to go see my mom up in Michigan, and she is still around, but it was a great chance to say goodbye to her. The doc says she'll probably be passing on within the next week or two. Okay, known series that converge. Well, we don't know too many that converge. We do know one that converges. This is frog jumping. We even know that it converges to 1. Okay, but this is an example of a geometric series. So, known series that converge is a geometric series with common ratio r meeting this condition. It's between -1 and 1. If that's the case, so here a common ratio is 1/2. When you multiply to get to the next term. And every geometric series, if the R meets this condition, it will converge. And then another one. Let me insert a little bit more space. Another one that we know that converges is if you have 1 over 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. This will converge. And this is a P series. So P series and its summation 1 over I squared. But the P series is summation 1 over I to the P power. P series with P. Now, what was the condition on P? P is like this. It has to be big enough. Remember, if P is 1, you just get the harmonic series. And that doesn't get small, the fractions don't get small enough fast enough. The sum goes off to infinity. They have to get small quickly with P greater than 1. Okay, those are the known series that we know that converge. Okay, and give me a little feedback on number 1. about the review on that. Anybody else having sound problems? Yoon, you can try getting out of Discord and get back in. Sometimes that clears things up. Okay, yeah, we're more familiar with the geometric series than the p-series. And all right, list the formula for the sum of a geometric series. And I'm going to give you a hint. A general geometric series looks like this. So the sum S, there was a formula we learned for the sum of a geometric series. "30 seconds more." So, let's suppose I kind of remember and kind of don't, and I guess. And I'm going to guess it's something like, it had to do with A and R. Those are only two letters in it. And maybe A, all right, over 1 minus R. I might check this and then I would say, all right, if that's what I'm remembering, it should at least work with this one, because we know this one converges to 1. So if I did this, then A, I'll try it here. The A is 1/2. 1 minus 1/2 is 1/2 over 1/2, which is 1. Oh, it works. So, turns out this indeed is the formula. And actually, the way we got that formula wasn't that difficult. I'm going to review it again. If we call this S, oops, this thing is S, because it's the sum. Then we multiply both sides by A. No, not by A. I think I made that mistake last time too. By R. Then the first term is going to be A times R, but instead of writing it right underneath here, I'm going to write it underneath this one. And this next term is AR squared, but I'm going to write it over here. And when it goes out forever, this technically is like has one more term than the, but no, it doesn't. They both have an infinite number of terms. And then if you subtract, you're going to get S minus RS. All these things cancel out. You get A. And you factor out the S. Divide by 1 minus R. This formula will work as long as R is meeting the condition. It's a convergent where the absolute value of R is less than 1. Alright. A little feedback on this formula for the sum of a geometric series. Okay, and all right, number 3, what's easier to show? That a sequence converges or a series converges. Which one's easier to do? So 30 seconds more. Just ponder it. Alright, turns out this is much easier for a sequence to converge. For a series to converge, it's much more difficult. And that's what this chapter is a lot about, is how can you show that a series converges. But a sequence converging is, we use that as a tool to help us with series conversion. Alright? How do we show that a sequence converges? You might give an example, you might state it in general, whatever. I'll give you a minute here. Okay, for a sequence to converge, well, let me give you an example, like 1 over 1 squared minus 5, comma 1 over 2 squared minus 5. 1 over 3 squared minus 5. 1 over 4 squared minus 5. This is a sequence, and we might wonder, does this converge? Actually, we tend to really be interested, and we usually ask for more than that. How do we show that a sequence converges to 0 is generally what we want. If the sequence doesn't converge to 0, then we use the divergence theorem to say, hey, we're not even going to bother with this series because the sequence doesn't converge to 0. And so one thing that we look at here is we could just kind of give a overall inspection and say, hey, the denominator is going to keep getting larger and larger and larger while the numerator is fixed. So this is going to 0. But ultimately, what we're really doing is we usually use the idea the primary tool for this is we use the idea of horizontal asymptotes. And so we might rewrite this in summation notation. I equals 1 to infinity. It's always got a 1 in the top. It's always got a minus 5 over here. And then when I is 1, 1 squared, I goes to 2, it's 2 squared. So this is I squared minus 5. And then we look at the function f of x is 1 over x squared minus 5. This function agrees with this whenever x is a whole number. When x is 3, you're going to get the same result as when I was 3 over here. And then this just goes through all the fractional points in between as well. And does this have a horizontal asymptote? Well, geez, well, of course not. This is, the degree of the denominator is greater than the degree of the numerator. No horizontal asymptote. Actually, the horizontal asymptote is y equals 0. So we see that that's our principal tool for showing sequences converging. Okay, and then, so it's way easier to show a sequence converge because we're usually just looking at it kind of as a horizontal asymptote. And how do we show that a series converges? I'll give you a minute for this. All right. 30 seconds more. All right. We only have a few things. How do we know that a series converges? If it's a geometric series, with absolute value of r less than 1, and we know it converges. If it's a p-series, with p greater than 1, that's summation I equals 1 to infinity, 1 over I to the p. That's a p-series. And it's kind of like when p is 2, it's kind of like this I squared and 1 over x squared. Okay, and then we have one other test, only one other test to show that it's convergent. We're going to get more, but as of right now we only have one. And does anybody know the name of the test that we can use to show that a series converges? Anybody?
I believe it's called the integral test.
Yes, the integral test. And we use the integral test when we see like the series in some kind of form that we can say, hey, that form looks like something that I could integrate. And so, I mean, sometimes they're so simple that you can, because it's like one of these or one of these or something like this. But if it's not one of those, but then you say, I think I could just integrate this, then we could use the integral. I'm not thinking of one right off the bat. So let me look one up real quick. Like this one. For some reason I put a table there. Well, I won't hurt it. E to the k over 1 plus e to the 2k. Here's one thing that, hey, if I replace those k's with x's, I could integrate that. And then I could say, all right, I could show whether it converges or not by the integral test. All right, so these last three questions were easier to show which one, sequence or series converging. How do we show a sequence converges? How do we show a series converges? A little feedback on that. Alright, let's get feedback. Okay, so the much tougher one is, how do we show that a series converges? Today we're going to learn another 2 tests to go along with this, besides the integral test, to show that a series converges. All right, number 6. Identify these series and state whether they converge or diverge. So, A. Okay, 30 seconds more. Alright, this one, if I had any problems with it, I would maybe write out the first few terms. 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus da 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 da. And this is a p series with p is equal to 3, and as long as p was greater than 1, it converges. Remember, if p is equal to 1, you get the harmonic series. 1 over 1 plus 1 over 2 plus 1 over 3, etc. Okay, the next one. Identify that. State whether it converges or diverges. Thirty seconds more. This is a geometric series. And what do you multiply to get to the next term? You can multiply by 1/4. Or you take any term divided by its predecessor term and you get the common ratio of 1/4. So it converges. Now most of the time we're not really interested in what it converges to. We're just interested that it does converge. But this is one that, since we can say what it converges to. Converges to a over 1 minus r, which is 16 over 1 minus 1/4, which is equal to 16 over 3/4, which is 16 over 1 times 4 over 3, which is 64 thirds, which is 21 and 1/3. That's what this gets infinitely close to. Okay, and then C. Identify that. State whether it converges or diverges. Alright, this one, if I just rewrote it, it's a P series. P is equal to 1/2. And P had to be larger than 1/2. This diverges. So this is also the summation I equals 1 to infinity of 1 over I to the 1/2. Okay, and then D. Thirty seconds more. To get to the next term, you multiply by 1/10. So this is a convergent geometric series. R equals 1/10. And do E. Thirty seconds more. This is an arithmetic series. The common difference is negative 0.2. It's what you add to get to the next term. But this diverges. Arithmetic series always diverge, only the trivial one with all zeros.
Mr. Shankin,
Yes.
for D, wouldn't R be 10, not 1/10?
You divide. Oh, thank you, thank you, thank you. These are getting bigger. not smaller. So this is a divergent geometric series. R is equal to 10. Divide anything by its predecessor, and you multiply by 10 to get to the next one. Yes. Thank you. And F. For what values of W will this series converge? $30 more. Okay, this is a P series. The W is just replacing the letter P. So when W is greater than 1, then it converges. Okay, give me a little feedback on all these in number 6. There's quite a few, but we were going over those known series and being able to identify them in different formats and make the right conclusions. A little feedback would be good there. Yeah, little things can be missed like that, Kylie. That's good. All right. So, questions? And let me look in Discord. You can type them in or speak them in. .4. Let's start with number 6. And explain why the sequence of partial sums for a series of positive terms is an increasing sequence. Alright, so let me take something that we know. 0.3, an example, plus 0.03 plus 0.003 plus da 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 forever. Okay, so sequence of partial sums. We call this one S1. take first two terms, you call that S2. Take the first three terms, call that S3. Now, why does the sequence of partial sums of the series is all positive? So there's no negatives in here. Why is it always an increasing sequence? So if we made S1, S2, S3, da da da, we get this sequence. 0.3, 0.33, 0.333, da 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 da. Why is this always increasing? Because whenever you add one more term, to go from like S2 to S3, you have to add one more term. And it's whenever you add a positive, you always get something larger. So it's always going to be increasing. Is that enough for number 6? Is that? Hit it? Alright, then let's look at number, let's go, still stay with 10.4, number 30. Here. So also from 10.4. Okay. Now, the instructions on number 30 was use the divergence integral or p-series test. Use one of them to determine whether this converges or diverges. Alright, so what I'm going to do is rewrite this. K to the e minus pi power. Because when the bases are the same, the rules of exponents is you subtract. Now, e is approximately 2.718. Punch it out in your calculator if you're forgetting. Pi is approximately 3.14. So when we subtract these two, we get a number about, this is approximately negative 0.4. Subtracting these two. And so, what is that? Is that something that is known or not? Well, all that review we did on these different kind of series hopefully can help you see that it's the same as this. When you bring it to the denominator, what do you got to do? You got to change the sign of the exponent. The sign of the exponent would change, and it would be pi minus e. But still now this is approximately positive 0.4 now, the bigger one minus the smaller one. And this is what we call a p-series. P being pi minus e, which is approximately 0.4. But how big does P need to be? P needs to be bigger than 1. So this diverges. P greater than 1 needed for convergence. Any questions on number 30 here? Okay, no questions there. Let me jump back to Discord. There's one more for 10.4, which is 16. Okay. Also from 10.4, and it says, use a divergence test. Determine whether it diverges or state that the test is inconclusive. All right, we need to use the divergence test. We take the limit as k goes to infinity, k cubed over k factorial. Now, as k gets really, really big, for instance, if, let's say, k is 100, you'd be getting 100 cubed, which is 100 times 100 times 100 over 100 factorial, which is 100 times 99 times 98 times 97 times all the way down to 1. Now, you see, these 100s will cancel out, and these will almost cancel out. 100 over 99, 100 over 98 is a barely bigger than 1. The denominator is just way, 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 way bigger than the numerator. So this limit is equal to 0. So, conclusion, divergence test can you feed Pepper and bring her to the other room? No, thanks. Oh, she's just gassy. Okay. My dog is, she gets seizures now and then. She just had one. Conclusion, divergence test tells us nothing. It can only tell us in the positive sense, when it tells us something definite, it tells us that it diverges, but it can't prove convergence. And so it passes the divergence test, but that doesn't really tell us anything about convergence. Any questions on 16? All right, let me number 8 on 10.3. That's on page 668. And number 8, I believe. Reindexes the series, so it starts at k equal 1. Alright, so this one, when you have it starting at k equal 5, the first term is going to be 3 over 4 times 5 squared minus 63. And then the next term is going to be 3 over 4 times 6 squared minus 63. And the next term is going to be 3 over 4 times 7 squared minus 63. So I'm writing out the first few terms of this. Now, it's trying to get you to see that the indexing can be whatever you want it to be. You can start at different letters. So, if we rewrote this, starting at 1 to infinity, how would I have to change this? Well, one thing that wouldn't change is there'd still be a 3 and there'd still be a minus 63, because that's in every one. There'd still be a 4. There would be something squared right here. But when k is 1, we need this to be a 5. So all we have to do is say k plus 4. And then when k is 2, this will go up to 6. K is 3, go up to 7, and so on. So we can change this back down to 1 if we want. That's why we don't get fussy at all about where these things start. Typically, it's like k equal 1 or k equal 0, but it can be anything. And we can reindex whenever we want. So that, any questions there? And number 24 from 10.3. Also 10.3, and the directions on this were evaluate each geometric series or state that it diverges. Alright, so if I was to write out the first few terms, this is negative 2/3. The next term is going to be positive because it's going to be to the second power, so that's 4/9. The next one's going to be negative. When I cube that, I get 8/27, and then plus, da, 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 da. I can see this. What do I have to multiply to get to the next term? This is a geometric series with r being negative 2/3. And when it's something to a power, that base is the r. And so we have this, so the directions evaluate the geometric series. So this geometric convergent series, because r meets the conditions between negative 1 and 1. And the evaluate the series, S is equal to A over 1 minus r. And the A is the very first term, negative 2/3. 1 minus, the r is also negative 2/3. So 2 negative, make positive. 3 over 3 plus 2 over 3 is 5 over 3. So it's negative 2/3 times the reciprocal. So I think somebody has unmuted. So if you could check your muting and then mute, and then we twos, and this result is going to be negative 2/5. If you add all these things together, back and forth, and it's what's kind of interesting with something like this is you can wind up doing this. Once you know what the series goes for.
Why
Yes.
A is not 1?
Why is the A not 1? All right, because you plug in k equal 1 and just find out what the first term it turns out to be. When k is equal to 1, the very first term of the series is negative 2/3, so that's the A. A is always that, not necessarily this index, but what the first term of the series turns out to be. All right, so now I'm going to look at this series in this perspective. I'm going to draw a little picture. And here's my n, and here's my a sub n's. And you see you had negative 2/3 plus 4/9 and so on. In fact, if we change this, instead of a sub n, let's change it to s sub n. So partial sums. So when n is 1, the first partial sum is negative 2/3. Okay, so let's come down to here. But before I start, I'm going to notice that the sum is negative 2/5. Now negative 2/5, divide this into 5 parts. Here's negative 2/5 right here. When you have an oscillating series like this, changes in sign each time, what's going to happen is your first partial sum, negative 2/3, will be on one side of this. So negative 2/3 is about here. Well, let me put an X, because I can't make dots very well in this. And then the next one, when I add 4/9 to it, it'll guarantee that I move to the other side of this. So it'll send me over to this side. And then when I subtract 8/27, it'll send me to the other side of this. And then I add the next term and it'll send me to the other side. But what will happen is we'll get closer and closer to this red dotted line, the sum of the whole series. And it's a very interesting way of looking at it. We'll just hug that tighter and tighter as we go out. Alright, so any questions on this one? And does that answer all the questions, the homework questions?
So far.
I have a quick question, actually.
Yes.
I'm sorry I didn't ask this sooner, but what you put like 2/3 when you were evaluating number 24. You put negative 2/3 as A, but shouldn't A be 1 in this case?
A would be 1 if this indexing was k equals 0. Then anything to the 0 power would be 1. But k,
Ooh, okay.
K is 1, so negative 2/3 to the first is negative 2/3. So the very first term in the series is negative 2/3. That's A.
Okay, thank you.
You're welcome. All right, anything else? Any other questions? All right, let's break here. We will start again. At 6:41 p.m. We'll learn about 2 more tests. They're called comparison tests. And how to show that a series is convergent. And does anybody need to speak to me individually before I take my break? All right, see you in a bit. All right, we will start up again. And we are looking at comparison tests today. 10.5. And this is, there's some overall things that we should look at. We really don't care about sequences. We care about series. And we don't care about divergent series, we only care about convergent series. So why in the world do we care about series that converge? This is what we've been spending, all this chapter on, is building up to being able to tell whether a series converges or diverges, and why are we so interested in this? Well, what we're going to learn is before the semester ends, you'll learn how to write functions as an infinite series. For instance, you'll be able to say that cosine x is the same as 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial minus, and so on and so forth. And this formula, let me just do a real brief exercise with you. Pull out your calculator, or use the calculator on your computer. Well, make sure you're in radian mode. So I'm going to check my mode on radian. And I'm going to take the cosine of now 0.35. Now, the cosine of 0.35. Now that's 0.35, not degrees, but radians. So remember, about 3 radians gives you 180 degrees, pi radians. So 1 radian is about 60 degrees. So 1/3 of a radian is still, it's around 30 degrees or so. Or 20 degrees, something like this. All right, so it's a fairly substantial number. Cosine of 0.35, if I punch it out of my calculator, I'm going to get 0.93937, and it keeps going. Now, let's look at this expression. 1 minus, and replace the x with 0.35. Okay, so, and I'm gonna keep looking at this, plus 0.35 to the 4th over 4 times 3 times 2 times 1 minus 0.35 to the 6th over 6 factorial, so on. All right, where this one is S1. Take the first 2 terms, you're going to get S2. Now, we first got to replace this. 0.35 squared divided by 2. this is 0.06125 for this whole term. And then if I take 0.35 raised to the 4th and divide it by 24, I get something even smaller. This is point 3 zeros. Alright, so my S2 is, if I take these first two together, so 1 minus that number is going to be point 0.93875. Notice S1 is larger than this result. Remember that graph that I was showing you? The sum of the whole sequence? This whole sequence right here is going to sum out to this. And this one is slightly above that. This one is slightly below that. And then if I add the next term to the sequence, I'm going to add S3 is equal to plus second plus sign. Alright. My S3 is 0.93937. It's a little bit bigger than this. It looks like it agrees with this, but look at how quickly it gets close to this. And it'll be a little bit bigger than this. And the next one will be a little bit smaller than it. And it'll keep squeezing in closer and closer to this. And this infinite series gets the same values as punching this into a calculator. And we're going to be learning how to do this. And, alright, now you might ask this question. Why would we write an easy function, cosine x, as something really hard, which is an infinite series? Even though these are nice, simple, little, small functions, it's still an infinite number of them. That's a lot harder than this cosine x. Alright, well, we typically do something like cosine x, only for teaching purposes. We use an infinite series, and only if it's a convergent infinite series. That's why we're so interested in whether the infinite series converges or not. We use infinite series to replace another function when the function is too difficult to work with. With the infinite series, we can replace the function with the infinite series, and we do that to take an integral, like if we can't integrate the original function, or to solve a differential equation, or to create a modeling function. And what we wind up doing is we wind up becoming very surprised in this theory is that you only often need like 3 terms or so, and you get very quick convergence. You get really, really close to your answer within just a few terms. And so the idea of, why would I use an infinite series that goes on so long? Well, you usually don't need very many terms at all. And we will find out how to be able to do this kind of stuff. But all of this theory works only if the infinite series is a convergent one. So that's why we are spending so long looking at how do you show that a series is convergent. All right, so that's a little bit of an overview, kind of about where we're going. And all right, we have 2 tests today. The first one is called the comparison test. And it says, let A sub k and B sub k be series with positive terms. Now, if the first series A sub k is always smaller than or equal to the corresponding elements B sub k, and a larger one converges, then the smaller one also converges. And vice versa. If we're talking about divergence, if the larger one, right here, if the one that's smaller, B sub k, diverges, then the one that's bigger than it will also diverge. And there's a note, this is from the textbook, I pulled this out from the textbook, whether a series converges depends on the behavior of terms in the tail. So the tail wags the dog. So the inequalities need not hold for all terms, they must hold after a certain point. So you might be able to ignore the first number of terms. Alright, so let's see what this means in the context of some examples. So, first example. 1/2 plus 1/4 plus 1/8, etc. We know that that is a geometric series. R is equal to 1/2, so it converges to 1. So, 1/3 plus 1/5 plus 1/9. Well, look at what this is. If you compare term for term, 1/3, this 3 is actually 1 over 2 plus 1. This 5 is the same thing as this one, but there's an extra plus 1. This 1/9 is the same as this 1/8 plus 1. So what are we seeing? Whenever you increase the denominator by 1, it makes the whole fraction smaller. All right. So when you compare them term for term, 1/3 is smaller than 1/2, 1/5 is smaller than 1/4, so on. So this one converges to 1. This one is even smaller, so it must also converge. And that's what it's saying. If the bigger one is known to be convergent, then this one that's clearly smaller than it, because we increased every denominator by 1, we made it smaller, then this one also converges. What's interesting to note is we don't know what this one converges to. the 1/3 plus 1/5 plus 1/9. But we really don't care. We just know that since it's term for term smaller than the other one, then it also converges. And so that's a use of this comparison test. All right. So what we're going to do is part B, show that this one converges. How do I show that 1 over I to the third plus 6 converges using the comparison tests? You have to think about that for a bit, and I'm going to have you work in your groups on this to show that this thing converges. And let me just have everybody go into your group chat and type in hi. Group leader, remind the spokesman of the day who they are. And let me just check real quick on the groups. Group 1, is anybody here? Let's go to group 2. How many of you are here? Group 3.
3 of us.
Pardon?
There's 3 of us in group 2.
3 of us, 3 in group 2. Okay. Group 3, how many here?
There's 4 of us.
4.
4.
And group 4, anybody here? Nobody here in group 4. Group 5, anybody here? How many are here? And if you don't have a mic, you can type it in. Group 5. Group 6, anybody here? How many here?
There's 3 of us.
3 from group 6. And group 7, how many are here?
There's 2 of us.
2 of you. Okay. All right. So, do part B. Show that that converges using one of the comparison tests, and discuss it in your group chat. I'll call on a group in a little bit. Okay, let me ask group 6. What do you got for this?
Someone said that since 1 over I to the third is a convergent in P series, that the series is always smaller than 1 over I to the third, so it will also be convergent.
Ah, very good. So, 1 over I to the third converges because it's a p series with p equals 3. And when you, like the very first term in this one is 1 over 1 plus 1 over 2 cubed is 8 and so on. But this one is 1 over 1 plus 6 plus 1 over 8 plus 6. So these terms are always smaller than these terms. 1/7 is smaller than 1 over 1. 1/14 is smaller than 1/8, so on. So this is smaller. All the terms here all these terms are smaller or equal to than a known convergent series. Now this smaller than has to be, they have to be positive. So this test only works with positive terms, because smaller than a negative number is, you could be hugely negative. So we only do this with positive terms and smaller than a known convergent series. Thus, it converges. Alright, it's got to be small enough to converge. And if it's smaller than a known convergent one, well then we know it converges. So it totally makes sense. Alright, C. Let me give you a small amount of time. Show that that converges. Okay, group 3. Can you get us started on this?
My group had said that maybe use 1 over
Lost you for a little bit.
hello?
Yes, try again.
Yes. Try again.
My group was saying that 1 over t plus 2, maybe?
T plus?
T plus?
1 over t plus 2, maybe. We don't know.
I'm sorry. I missed in my chat. I was considering t plus 3. 1 over 3.
1 over 3 plus 3.
Okay.
Okay.
The communication. We're getting a bunch of echoing now. So go ahead and mute.
Go ahead and mute.
Alright. Let me. I think people are muted now. Yeah, some of the mics are having a hard time here. So if this didn't have this plus 4, if we were just doing I equals 1 to infinity of 1 over 3 to the I, what would we wind up getting? 1/3 plus 1/9 plus 1/27. This is a known convergent series. This is geometric. With r is equal to 1/3. And then when you add 4, you increase every denominator. And now, we're looking, is this thing small enough to converge? Well, it's even smaller than a known convergent series. So it's smaller term by term than this geometric series right here. Thus it converges as well. Alright, now by the way, when you're doing this in homework problems later on and we have a whole bunch of tests available, like we had the integral test or this or that, you have to state the name of the test. So I'm kind of skipping that. I really should say convergence test. Write the name of the test, of what you're using, and then show how it's meeting these conditions. It's smaller than a known convergent series or bigger than a known divergent series. And that's what all this is. Smaller than a known convergent series or bigger than a known divergent series. That's the divergence test. That's the comparison test. All right. So, go to D. Show that one converges. I'll give you a minute in your groups. All right, group 2. How do we show that this converges?
We can divide all the term to by the k to the third.
Okay. Like if we eliminated all the terms other than the k to the third terms?
Yeah.
Okay. Summation k equal 1 to infinity. K to the third over 4k to the third. Suppose we got rid of all the rest of them, because as k gets really, really huge, they become super small compared to the bigger power. Okay? What next?
Then we go 1 over 4.
Okay? So does this converge to 1/4?
Yes.
Converges to 1/4. All right. This is what I would think of at first, too. But we made a classic mistake that's really easy to make. If this, instead of summation, if this was just this, if it was just a sequence, which is equal to, when it's 1, you get 1/4. When k is 2, well, you always get 1/4. You get 1/4. You get exactly 1/4 every time. This one definitely converges to 1/4, but it's a sequence. Now this one is a series. So what I did is I gave you a trick question. I asked you to prove something that was false. This does not converge to 1/4. The sequence converges to 1/4. But what has to be true about the sequence? The sequence has to converge to 0 to give the series a chance to converge. An infinite number of 1/4 added together goes off to infinity. So the sequence converted. Another way of stating this is the limit as k goes to infinity of k cubed plus 7k squared minus 3k plus 1 over 4k cubed plus 2k minus 6 is equal to 1/4. By the divergence theorem, this series diverges. It never had a chance. The sequence didn't even go to 0. So I'm going to be doing that every now and then, tricking you all, telling you to prove something that isn't true. Hopefully this reviewed and kind of reinserted, oh yeah, the divergence theorem is something that we always have to kind of, we use to sift out the big rocks whenever we're looking at a series. And we say, don't even bother working with this one because it doesn't even pass the divergence theorem. Alright, let's go to E. Show that this one converges. And use one of the tests we have so far. I'll call on a group in a minute. Okay, group 7, what do you have for this?
I think that at least from what we know, we can't show that since, like, if you use the, what was it called, the comparison test, we can't use that since it's 1 over I cubed minus 6, and so sequence A is actually larger than sequence B.
Very
Or-
good. Very good. So if we had the summation I equals 1 to infinity of 1 over I cubed. Now that's equal to 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, 1 over 4 cubed. Now when we do this minus 6. We're making each fraction bigger. Like this one, instead of 1/8, is now 1/2. When you make the denominator smaller, you make the fractions bigger. And so we have this. We have a known convergent series right here. This is a p series with p is 3. But this is larger than a known convergent series. If it was smaller than a known convergent series, we could say, thus it must converge. Thus, no conclusion. You cannot prove that this one converges by the comparison test. This comparison test only works if you're making the fractions smaller than a known convergent series. If you make it bigger than it, you cannot use that test to prove convergence. All right, but we can still show that this thing converges, because it makes sense that it should converge. This is going to essentially act like the other one. And just because we, put a minus 6 instead of a plus 6, when the numbers get really big, it's not going to make much difference. This is still going to converge. We should be able to show that this converges, but we can't do it with the comparison test. But we can do it with the next test. It's called the limit comparison test. So this problem, we would say it needs the limit comparison test. And let's look at it. This is directly from the textbook. So again, these are two series, A and B. All the terms are positive. And remember, the only series that we're going to wind up ever looking at is if they're all positive terms or if they rotate from plus to minus, alternating series. And most of the time we'll be looking at all positive terms. So now this one is, instead of saying that one series is smaller than the other, this is saying that when you take the limit and you put the two series as a fraction, and you find this limit and you get a number, a value L, then if L is, number 1 is basically saying that if L is finite and it's not 0. With all positive terms, L is never going to be negative. But it's not 0 and it doesn't go to infinity. Then these two series both do the same thing. If one converges, the other converges. If one diverges, the other diverges. Either both converge or both diverge. And then there's a couple exception cases, but we'll talk about that a little later. The main thing is number 1. So we make a fraction out of the two series, and then we find the limit, and if we get some number L that's finite, then we say it's they converge or diverge together. Right, so let's look at this. Let's show that this series converges. This is the one that we were just looking at, that We couldn't do with the convergence test, but with the limit comparison with the comparison test we couldn't do it. But with the limit comparison test, we can. This is going to be one of my either A sub n or B sub n's. My other one that I'm going to compare it to, I'm going to compare. Oh, first of all, we write the name of the test. When you're doing, like, especially on a, on an exam, we'd write, we're going to be using the limit comparison test. We're not using the integral test or, some other test. You've got to orient me, otherwise I'll be totally confused as to what you're doing. State the name of the test that you're using. We're going to, then we say we're going to compare to another series. Now this series is not a known convergent or divergent series. It would be if it didn't have this darn -6. So we're going to compare it to I equals 1 to infinity of 1 over I cubed without the -6, which is a P series that converges. So we were trying to do that up here, but we had the problem because it was larger than it rather than smaller than it. Okay, and now what we're going to do is we're going to take these two. One of them is going to be thought of as A sub n, the other is B sub n. It doesn't matter which is which. We're going to take the limit as I approaches infinity of one of these over the other one. And it doesn't matter which one goes on the top, which one goes on the bottom. Doesn't matter. Okay, now these limits, this is the limit of a sequence. These are easy to find. It's basically kind of looking at horizontal asymptotes. This is the limit as I approaches infinity. Copy dot flip. So this one flips over and you get I cubed over I cubed minus 6. Now, as I gets really, really big, the one with the greater degree dominates, but they have the same degree. So the 6 becomes inconsequential as I becomes, a million and a billion and all that stuff. And you get the I cubes cancel out. The ratio of the leading coefficients is 1, which is equal to 1. Now, conclusion. With any of these tests, I want you to put conclusion at the end. Now, since the limit was 1, doesn't the limit have to be 0 for the series to converge? So shouldn't we say this diverges? No. This is not. What we're doing is we're taking the limit of one over another, the two series, and when we put them one above the other, and we take the limit, we're saying, do these essentially act the same? Now, if we'd have gotten infinity or 0, like for instance, if I'd have compared this to I to the 4th, 1 over I to the 4th, then I would have gotten I to the 4th over I to the I cubed minus 6, and this would have gone to infinity, and then these two things don't move together. They don't converge or diverge together. But since I got something that was not 0, not infinity. L is finite. Then these two things both converge or both diverge. Conclusion. Let me shrink it up so I can see all this. And without putting the indexes. These two converge or diverge together, because that's what the theorem says. As long as this L is not 0, it's not infinity. But this one we know converges. So they converge together. Thus, converges. All right. This one, because it made all the fractions bigger, we couldn't use the convergence test, the comparison test. But we could use the limit comparison test. And that said that it essentially acts the same as this other convergence series, and thus it also converges. Any questions?
I have a quick question.
Yes.
Rowan.
Okay.
So with the one we just did, don't we get negative values in this sequence? And so how does, like, when I is equal to 1, we get negative 1/5.
Yes.
So how does that, because doesn't the rule say they all have to be positive?
Yes, and they also has a little thing to the left of it, which applies for both. Whether a series converges depends on the behavior of terms in the tail. So the inequalities need not hold for all terms of the series. They must hold for all k for some positive integer, and same with the conditions. The conditions, them being all positive, must be all positive after some point. So we get to go, I'm glad you brought that up, because we technically didn't meet the conditions of this, be series with positive terms. But actually we can be all positive terms after some particular point. And then it's the tail that determines everything else.
Okay, thank you.
You're welcome. All right, so let's go to B, which is significantly tougher. Show that this thing converges. And we're kind of running out of time, so let me cut right to the chase. We're gonna, now when I do this, there's two choices that I have. This series right here is essentially this series. Now, when I gets really big, the -4 and the +1 become inconsequential. And the I and the I cubed are going to reduce. It'll be like I squared down here. Now the part that you have a choice about is some people say that this is essentially 3 over I squared. And some people say this is essentially 1 over I squared. And it doesn't matter whether you put a constant, multiply by a constant or not. All right, let's just say it was essentially 1 over I squared. So these are the two things that I'm comparing. And now I'm going to state the name of my test. I'm using the limit comparison test. It's So these are the two. And after a while, they'll all have all positive terms. Like when I is 1, this is going to have a negative term and so on, but it doesn't really matter. And so we're going to take the limit as I approaches infinity. We're going to this limit comparison test. We're just taking the ratio of these two, and it doesn't matter which one you call A, which one you call B, which one you put on the top, which one you put on the bottom. You just put one of them on the top and one of them on the bottom. And this over this. Equals the limit as I approaches infinity. Copy dot flip. Okay, now as I goes to infinity, the smaller degree terms just become inconsequential. The I cubes cancel out, and this ratio just becomes 3. Now, by the way, if I hadn't have chosen the right one, if I'd have chosen like 1 over I instead of 1 over I cubed, then this one would have been I to the, instead of I to the second, it would have been I to the first, and I would have a smaller degree in the numerator than I have in the denominator, and this whole thing would go to 0. And if it goes to 0, then you don't say that these things converge or diverge together. Alright, and this, it's essentially this, which is a P-series convergent P-series. Okay, and we get this L, and since L is not 0, and it's not infinity, it's anything in between, it's finite. Then we say, by the theorem, by the limit comparison test, thus these two must converge or diverge together.
So
Yes.
I know you said the leading coefficient doesn't matter, but if you were to use 3 over I squared,
Yes.
since technically it's 3I over I cubed,
Yes.
it would be 3 over I squared. Wouldn't the limit be 1?
That's right. If we'd have used a 3, in the end we would have gotten a 1.
So does that matter?
No, because in the test, all you have to do is L cannot be 0, cannot be infinity. Doesn't matter what number L is, as long as it's not 0 or not infinity. If it's not either one of those, then they converge or diverge together. So getting a 1 or a 3 doesn't matter. Okay? Does that make sense, Kylie?
Yes, thank you.
You're welcome. All right. Since L is not 0 or infinity, the two series converge or diverge together. But one of them was a known convergent series. So this part is gone. They converge together. Thus, the one that we're looking at. summation 3i plus 1 over I cubed minus 4 converges. So I'm glad you brought that point up. What we get doesn't matter. The number that we get doesn't matter. Now in other situations, the number that we got really matters. Geometric series, if it's less than 1 or bigger than 1, it really matters. But in this case, no. It's just as long as it's a finite number. L is finite and positive. All right. Now, the case 2 and the case 3 are some kind of special cases. Many textbooks don't even have these. It just has case 1, and that's it. But it's saying if L is 0, now if L is 0, it could be the case that L is 0 because the A sub k was all zeros. And then 0 divided by anything is 0. So if L is 0 and B sub k converged, then summation A sub k could converge. And if L is infinity and B sub k diverges, then summation A sub k diverges. We rarely ever use 2 and 3. If you just put your focus on 1, that'll be fine for the problems you'll be doing. All right. So let's go to C. Show that this thing converges. All right. So this is essentially, we're almost out of time here. Whether you put that constant in there or not doesn't matter. Whether you call it square root of 2n or square root of n, you'll just have it go to a different number as long as it's finite, doesn't matter. Now, if you do this, this is equal to the summation of 1 over n to the, because that's 1/2. Subtract the exponents, and so it's 1.5. And this is a known convergent p-series. So we could take this and this, take the limit. Oh, so first of all, you state the name of the test. Limit, comparison, test. Now, it's possible that I might be able to use the comparison test, but it has to be compared in the right direction. If we're making the fractions a little bit bigger instead of a little bit smaller, then you can't use it and so on. So in practice, nobody really uses the comparison test. It's just there to kind of introduce the topic. In practice, people just jump right to the limit comparison test and say, oh, once you get that down, it always works if you're comparing to. Now, we only use this when something that we're looking at boils down to or is essentially a geometric or a p-series, because they're the only two that we know converge. So it's got limited uses. But when it's essentially one of those, then we can use it. So we take the limit as n approaches infinity. You put one of these over one of those, doesn't matter which one where. limit as n approaches infinity. Copy dot flip. This bottom one flips over. The n squareds cancel out. This is the same as the limit as n approaches infinity of square root, and get rid of that. Two n over n becomes 2 plus 1 over n. So break it into two fractions. As n goes to infinity, it drives this to 0. And by the way, if when we were picking them, we had picked a 2 inside this square root, we'd be getting a 1 right here instead. So it doesn't, you know, as long as it's finite, that's the big deal. It's not 0 and it's not infinity. Thus, these two L is not 0 or infinity. They converge or diverge together. But this was a known convergent series. All this possibility is out the window. They converge together. Thus, summation, can't remember it, square root of 2n plus 1 over n squared converges. Okay. And the very last one. We're run out of time. It was a trick question. This one is essentially the 3 goes away, essentially 1 over I, which is a known, this is the harmonic series, known divergent series. So we could wind up showing that this diverges by showing that when you take the ratio of this over this, the limit as n goes to infinity, you're going to get not 0, not infinity, you're going to get some L in between, then they both diverge, and then you'll get that that one diverges. Alright, so the homework is 10.5. And I will see you all on Wednesday, and then the week after this week, we only have class on Monday. The Wednesday right before Thanksgiving, there's no class. And you can see a new schedule that I posted. All right. Let me stop the video.